In this video, we're going to look at yet another way to approximate a definite integral, and this time is something we call the midpoint rule. So remember, with left and right Riemann sums, what we did is we just drew rectangles on various subintervals of the same width, but we drew the height at the left or the right end of the interval. So a left Riemann sum, for example, here on the first interval would be, on this last interval, left would be drawing the height here. And we'd be finding a rectangle like that and doing that on each piece. The right Riemann sum would be drawing the rectangle up here. So we're choosing the height at the right endpoint or left endpoint. Well, what if instead we choose the height right here, right in the middle of the interval? Okay, and then we do that, then we get what we call the midpoint rule estimate, or I'll call that estimate M for midpoint. It's the midpoint of the interval horizontally that we're using. Now, we're still going to use intervals of the same width, so delta x is still b minus a over n, where we have n is the number of intervals or the number of rectangles. Now this time we take the right Riemann sum, the way we put the x at the end of the right interval was to let x be a plus k times delta x. But what we want to do is we want to take that and subtract a half of a delta x from that to move over back. So if this is here's a is here, a plus delta x, a plus 2 delta x, a plus 3 delta x, then we got to go back a half of a delta x to get to the middle of that third one. So I factor out the delta x and I get k minus a half times delta x. Okay, now what if we use that new definition of x sub k, a little bit different than we did for the left or right Riemann sums, then the sum here looks exactly like it should for the right Riemann sum. We're going to sum from 1 to n f of x sub k delta x, and we've done this so that when you plug in k as 1, notice we're moving over half of a delta x to get to the to the middle of the first interval. K is 2, we've gone over 1.5 delta x's, that puts us in the middle of the second interval, and so forth, to find the height of it there times the delta x. So that's our general formula. So what does that work out to be in this particular case? Well, let's see, we're going from 0 to 4, so 0 to 2, excuse me. So 2 minus 0 divided by 4, okay, is 1/2 for delta x, and a was 0, so this is just k minus 1/2 times another half, and I distribute the half, so it's 1/2 k minus 1/4. This should be from, fix that, come on. That should go from 1, then just go from 1 to 4. Okay, and so let's plug this in. So if you plug in k is 1, you get 1/2 minus 1/4 is 1/4, or 0.25. Find the height there, which is 0.25 to the 5th. Then we plug in k is 2. Half of 2 is 1. Minus 1/4 is 3/4, or 0.75. Take that to the 5th power to find the height, because our function is f of x equals x to the 5th. Then move over another half, a delta x of 1/2, we get to 1.25, evaluate the function there. Move over another half, evaluate the function there. In this case, since the delta x's are always the same, I can factor that out. The 1/2 work out all the arithmetic here, and you get 9.8515625. Okay, so we've been looking at sort of two functions. We've been looking at x to the fifth, but we've also been illustrating what's going on here on this particular cubic. This particular cubic is y equals x plus 3 times x minus 2 times x minus 1. And I have a particular interval here. I find the midpoint of that interval, go up to the curve, find the height, and it looks like that rectangle. Okay? So, pretty straightforward. Well, at first glance you might say, well, that seems to be very similar to the left or right Riemann sums, and of course it is. But it's also similar to the trapezoid estimate, which we could also think of as a rectangle drawn at some height in there. But this one is also not only a rectangle drawn at the height, we can also think of it as a trapezoid like we did in the trapezoid rule, but a slightly different trapezoid. This time what we're doing is, instead of drawing the secant line from this point to this point, we draw the tangent line in the middle. Now, since we know it goes up to the top of that tangent line, we know that point's in the middle, so we know the distance from the left side to that midpoint and from that midpoint to the right side is the same. So those two line segments are the same length. This is our tangent line segment. These two angles are vertical angles, so they're congruent, and these two are right angles, so they're congruent. We see that those two triangles now are congruent by the angle side angle theorem from geometry. So, in a manner similar to the trapezoid, we can cut off this triangle, rotate it over, put it on top of this triangle right here, and we see that the area this trapezoid formed is the same as the area of the rectangle. So, the midpoint rule gives us directly gives us a rectangle here, but it's also the equivalent to the area of that trapezoid. So, compare and contrast with the trapezoid rule gives us a trapezoid going from endpoint to endpoint here, or to points on the curve, so it's a tangent line, a secant line across here, whereas the midpoint rule gives us a tangent line in the middle. So secant line at both ends for tangent rule, trapezoid rule, tangent line in the middle for the midpoint rule. Or rectangles, midpoint rule gives us a rectangle where we take a point halfway in between horizontally, find the height there. Trapezoid rule, you take the left and right values, find the height in between those vertically, and draw your rectangle there. So, we can illustrate the midpoint rule back as a sum of trapezoids. We've been doing this with Graphmatica. Graphmatica does not have this one built in, but here it is as trapezoids with the midpoint of each one, and this is back to the function y equals x to the fifth power, and we're finding it from 0 to 2, and we go to the middle of the interval and draw our tangent line there, and we have a right trapezoid here, another one here, another one here, another one here. And so this gives us our trapezoid estimate. Okay, and we're going to look at comparing left and the trapezoid and midpoint estimates and see if we can further refine it to get an even better estimate, and we will, and it's going to be called Simpson's rule, which we're going to use in the next video.